So in this related rates question, we read that a conical container is 30 inches high and the radius at its top is 6 inches. If it is filled with water at a rate of 15 cubic inches per second, find the rate at which the water's depth is changing when the depth is 18 inches. Okay, so what we've got here, something that looks like that. We got this conical container here. Now, in terms of what we know, well, we know a few things. First of all, we know that the height of this thing is going to be 30 inches. And we know that the radius is, at the top here, is 6 inches. Now, turns out that's important here. I'm going to zoom in just a little bit. We'll come back to this in just a second here to describe or to discuss why that's significant here. We are looking at, it's being filled with water at 15 cubic inches per second. Now, we're talking about the volume of the cone here. Well, I know that the volume of a cone is 1/3 pi r squared h. Okay, there's my cone. I know that the volume of water in that cone is increasing. It's positive 15. Oh, whoops, not why I made an M there. Positive 15 cubic inches per second. Okay, what else do we know? We know we are given a specific instance here where the water's depth, we want to know how fast. We want, what we want over here is how fast the water's depth is changing, or that's going to be the height of the cone of water, if you will. The height of the container's not changing, but the height of the water, like we're going to put water in here, okay, its height will change. Okay, so it's got this little radius here. This height is changing. This is what we're talking about right here. This equation here for the volume of the cone is this part right here. We are looking for that right there, and we're looking at it at the specific moment here when the height or the depth of the water is 18 inches. Okay, so now what we're going to do here, come down here, we're going to look at that equation that relates the variables we're interested in here. Now, we know how fast the volume is changing. We're interested in how fast the height is changing. So our formula here is volume is equal to 1/3 pi r squared h. Now, I would jump in right away here and take the derivative of this, but I've actually got two variables, both of which change in time. Okay. It would be great if this was in terms of just one variable. Now, I can still do this, because I can use the product rule to take the derivative of this. However, if I did that, remember that I'm taking the derivative, this is a related rate, so I'm taking the derivative with respect to time. So if I was to take the derivative of this right now, using the product rule, taking the derivative of both variables here, I would end up with, at some point in here, a dr by dt. Okay? I don't know what dr by dt is. I do, however, know what, I'm interested in what dh by dt is. That's what I'm looking for. I want that to pop out, but I don't really have any information about the radius here. So what I need to do here is I need to come up with some sort of relationship between r and h so I can kick out the r, okay, one way or the other here. And actually, that comes from the diagram right here. So when I draw this line straight down here, what I end up with are two similar right angle triangles here. This large one that has a height of 30, okay, and its length along this base right here is going to be 6, and this one right here that has a height of h, okay, because I don't know how tall that is, and it's actually, I've written it right up against the line there, so it's a little hard to see. There's my h, and then I've got this radius r right here. Those are similar triangles, and if it's hard to see, just kind of rotate this thing like that. It might be easier to see like this. In any case, what I know with similar triangles is that when I've got kind of corresponding sides here, they're in proportion. So this length is proportional to this one. The height of the whole thing, which is 30, is proportional to the height of this little guy right here. So there's a ratio we can build here. Okay, 6 to r, okay, base of the triangle, compares to the height of the triangle, 30, height of the little triangle, h. So now I've got this nice little ratio right here I want to get rid of one of these variables here. Now, I want dH by dt to pop out of the equation, so I want h to survive. It's r that I want to get rid of. Okay, so what I'm going to do is I'm going to solve for r here, and I'm going to do that by cross multiplying to start off with. So 6h is going to equal 30r, and then I'll divide, and we'll get that r is equal to h over 5. So that's the relationship. That is now what I can use to replace the r in this equation. Okay? Because at any given time here, the radius is going to be 1/5 the height. So now I can rewrite this and make this 1/3 pi h over 5 squared times h. Okay, well now I've got an expression in terms for volume here that's in terms of just h, and I love that. That's great. Okay, because now when I take the derivative, I'm going to get the dv by dt popping out, which is good. I know what that is, and I'm also going to get the dh by dt popping out here. So when I simplify this, we are going to get pi h cubed all over 75, and this is my volume. All right, now I'm good to go. So my derivative, dv by dt, because remember, I got to take this implicitly. I'm taking the derivative with respect to time. Time does not show up as a variable here. So I'll bring down the 3, okay, 3 pi h squared dh by dt, and this is still over 75. So I did the chain rule right there, brought down the exponent, dropped the exponent by 1, and then I took the derivative of what was inside. I don't know what that is. That's what I'm looking for. Good. Now I can substitute in the specific value the values that I've been given. I can't do this even for the height. I cannot plug in that value of the height, that 18 inches, until I've pulled up the terms that deal with how those variables change. If I was to plug in that h right here, that 18, this whole thing would become a constant value, and its derivative is just 0. It goes away. I learn nothing. So here, I can now plug stuff in. I know that my volume was 15, okay, 15 inches cubed per second. 3 pi, my height at the moment that we're looking for is 18. That'll be squared. This is all over 75. And I'm looking for dH by dt. And so now it's just a matter of moving stuff over. Okay, so I'm going to go to my calculator here. This is going to end up being, I'm going to take 15, multiply that by 75 in the denominator, then I'm going to divide by 3 times 18 squared. I'm not expecting this to be a nice value here, but calculator will convert that to a fraction for me. That's pretty nice here. And so I will get 125 all over 108 pi. Okay, because remember there's a pi over there, I got to bring that over. And this is going to be inches. Okay, whoops, sorry, we're finding, dH by dt, inches per second is our dH by dt. And that makes sense here. The volume is going to be, the volume here is going to be inches cubed, and the height here is just in inches, but I squared it, so inches squared. When I divide that out, I'm just going to get inches, and away we go. Now, I'm going to convert this to a decimal here just so that we've got it. So this number is great. It's important. I want you to be able to write these things in exact form. Yeah, but you know what? It probably is easier for you to get your head wrapped around something like this. 0.4 inches per second. Probably can see that a lot clearer than you can see the 125 over 108 pi inches per second. Okay? And this is approximate because I had to round that. Okay, there you go.